All right, what's going on, everybody? It's Friday night, and the best thing to do on a Friday night is to review your note cards. So, today we're going to be talking about limits in Calculus 1. And let's just jump into it. I mean, limits are a little tricky. They're a little notorious for being difficult or confusing, but we're going to break them down, make them intuitive, and you're going to see that they're just fine in the end. So let's do it. So let's define a limit. Now bear with me through this definition. So this says, let f be a function defined on some open interval about x equals a, except possibly at x equals a. And then we say, the limit of f of x as x approaches a equals L, if and only if, for all epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Now, to the two people that haven't clicked away from this video to watch some fail videos, I just want to give you a little applause. And I want to say that your perseverance is going to be rewarded because we're going to break this down and it's going to make sense. So, first of all, define a limit. What is a limit? It's just a number, right? It's like an operation that you apply on a function and it just gives you a number. So here we say the limit as x approaches a of f of x equals L. L is what we call the limit or the number. And so we have a function. And all this is saying is we're going to make the input to the function really close to this number a. And if we can make the output of the function as arbitrarily close as we want it to L, we're just going to say that L is the limit of that function as x goes to some number a. I think the reason that limits get confusing is because we introduce all these other symbols, like we have the epsilon here and we have the delta. And they're not even like letters that you're used to. They're these wild Greek letters, or they're strange symbols, man, and it's confusing. But it doesn't have to be. So let's just keep moving on here. This is the definition. And let's jump into an example actually to make it make sense. So let's make a function and make it really simple, like x. It's just x. And then we'll graph it. We'll look at the xy plane. And so we could say, like, let's make our a in that definition 4. And we could say as the input of the function gets closer to 4, the output of the function gets closer to 4. And so 4 would be the limit of this function as its input gets closer to 4. That's it. Let's try a different function like 2x. Now we would say, okay, the input of the function, as that gets closer and closer to 4, it looks like the output of the function gets closer and closer to 8, right? And we can see that over here as if we move closer to 4 right here, 3, 4, the output of the function is 1, 2, 3, 4, 5, 6, 7, 8. It seems to be close to 8. So that's it. That's all a limit is. The limit of the function 2x as x approaches 4 is 8. That's all that definition is trying to say. Now let's make it more complicated. So now we have to think of it like a game, basically. So this stuff down here, someone is challenging you to make the output of the function close to L. That's what this absolute value does. It's basically like the distance of the output of the function f of x and the number L. So this is the distance to L. Someone is challenging you. They're giving you an epsilon, and they're saying, make the output really close to L. I dare you. And then you're like, no big deal, right? I can restrict the input. That's what you can control. So you're like, yeah, no big deal. You give me this epsilon. I'm going to give you a delta. And if you restrict the input to the function, if you make this distance to this number a, if you reduce this distance to be less than delta, then you should be good no matter what epsilon you pick. So that leads us into something called an epsilon delta proof. Okay, so the epsilon delta proof, we have a function here, 3x plus 1, and we're saying the limit as x gets closer and closer to 4 of this function, we're going to say, well, the limit of this is 13, but we have to prove it, right? So you may think, well, it's kind of obvious. If we just plug x in, we're going to get 3 times 4, which is 12, plus 1 is 13. So it's kind of obvious, but there's a way to prove it symbolically if you want to be really technically correct. So the proof is kind of formulaic, but basically you always start with the challenge, right? This line, let epsilon be greater than 0. Somebody's going to challenge you and say, make the output of the function as close to 13 in this case as you can. And you're going to say, no big deal, because I'm going to make the input as close to 4 as I want it to be. And you're going to call that delta. And then for reasons, you're going to choose delta to be the challenge epsilon divided by 3 in this case. And if you do that, you just substitute it in, multiply both sides by 3, distribute the 3 inside the absolute value, break this up into two things, because plus 1 minus 13 is the same thing as minus 12. And then you see, here's the output of the function, here's the limit, and it's less than the guy has challenged you with, right? He said make this distance be less than epsilon. It's done, I win, right? So you're good, proven. So the limit of this function as x is closer to 4 is 13. Now the trick is, how do we know how to choose delta to be epsilon over 3, right? Well, I made a note and it just says for linear functions, choose delta to be epsilon over the slope. So a linear function is a function that just looks like a line, and m is the slope in like a y equals mx plus b, if you're familiar with that. So this works all the time for linear functions. So let's take a look at that, because that's kind of cool. So let's make our function general and just say that it's f of x equals m times x, and we'll get ourselves an m. And so now we can change the slope of our function, right? And we're going to say, let's make an a, right? This is what x is getting close to. Let's say it's 3. And so we're going to see what our function gets close to, or is, at 3. And right now it's 2.93. So for this slope, that's our limit. So we'll just graph that, f of 3. And then we're going to give a restriction. Somebody challenges us and says, make this output be within 1 of the limit, right? And we'll graph our restriction here. So we're going to say it's f of 3 a plus e and minus e. These are our restrictions. I'll make them be red. And so the output of the function for a given input has to be between these two restrictions, right? That's given this epsilon. And they can tighten it up. They can say, you got to be within half a unit of the limit, right? But for now, we'll just keep it as 1. And so we're saying, hey, no big deal. We're going to make our delta your epsilon divided by the slope. And so if I graph those as vertical bars, we're going to get, let's see, a plus delta. And we're going to graph the other restriction on the input. And we'll make those, I don't know, blue. And so now we're safe, pretty much, right? If we stay within these blue lines, notice how they intersect with the restriction, the red lines. If our input to the function stays within these boundaries here, the output is going to stay within the red lines, no matter what they do. If they want to tighten up on this, if they want to tighten up on the restriction, notice how our restriction on the input follows theirs and will always be good. Will always be as close to the limit being this horizontal line here at 2.93 will be as close to that limit as they want, and we're always safe. And what's good is, for a linear function, as the slope changes, notice how our restrictions change on the input, right? The restriction on the output stays the same, but as the slope gets steeper and steeper, we have to restrict the input more because the output's going to be changing faster, right? And as it gets more and more narrow, we actually have more wiggle room. And the input to the function can be anywhere from back here all the way up to here. And we'll still be close to the limit. And so the limit is changing as well. As I change the function, it's going to have a new limit. But we're going to stay within whatever this guy challenges us with these red lines, right? So that's the basic idea of a limit of a function. Somebody challenges you with the red lines. We come back and respond with the blue lines. For linear functions, we're like, hey, we'll just make our input restriction be epsilon over m, epsilon over the slope. And for other functions, it gets a little more complicated. So let's keep moving here. Let's take a look. I think I have a few more definitions, and then we'll actually evaluate some limits. So let's just go through these definitions. So this is basically x approaching the input from numbers smaller than the input, or x approaching the input from numbers larger than the input, right? Because we're getting closer to a. We don't actually ever have to get to a. And that's an interesting thing about limits. You don't have to, if you plug in a and you get another number, that you can still have the limit be a different number where you just get closer and closer to it, but you never actually plug in a directly. So we'll see that later, maybe or maybe not. You may have to look at that yourself. All right, so this is just saying we're approaching from the left side or the right side of A. And for f to have the limit be L, it's got to approach the same thing. It's got to get closer to L from both sides. Okay? The precise definition of now we're making x arbitrarily large or making x arbitrarily small. So we could look, let's look at a function like, well, let's look at this function we have right now. If we made x arbitrarily large, the output would just get arbitrarily large, right? Or if we made it x large negative, the output would keep going down and down and down and be large negative. And we could swap that if we change the slope to be negative. But that's the kind of limit we're talking about now. Now we're not approaching some specific input. We're just making x really large, positive or negative. And so we'll look at the definition. So f is defined on some interval, a to infinity. And we're saying for every epsilon greater than 0, this is the challenge, there exists an n such that if x is larger than n, then the distance from the limit of the function's output can be within epsilon. And if that's so, then we're going to say that the function has a limit, and the limit is L as x approaches infinity or negative infinity. So that's basically why there's two copies of that same definition. So let's look at, well, let's look at the intuitive definition first of that same thing. And all it's saying is we can make the output as close as we want to L by making x really large. Or over here on this case where x is going to negative infinity, we can make f of x really close to L by making x really large, negative, going towards negative infinity. Okay. So let's look at a function like, I mean, this is going to be kind of cheating, but 1 over x plus 2, and graph it, f. So if I asked you, what's going to happen to the output of this function if I make x get really, really, really huge, and you're going to say, well, screw you, I'm not even going to think, I'm just going to plug in numbers, and we'll try 100, okay. It's getting close to 2. Bigger number, oh, it's getting really close to 2. And I'm going to say it's 2, right? As I plug in really huge numbers in this function, the output seems to be going to 2. So we would say that the limit of 1 over x plus 2 as x goes to infinity is 2. And on the other side, if we plug in a large negative number, it looks like, in this case, as x goes to negative infinity, the limit of this function is 2 as well. but there's ways to prove it, and we'll see that in a moment. But that's the idea of these x getting really large or x getting really negative. Now we're moving on. This is a different idea. We're just going to say, okay, definition of an infinite limit at infinity. And I want you to just take a moment and appreciate how strange this sounds. An infinite limit at infinity. I feel like I'm losing my mind here, but let's, it makes sense. All it's saying is we can make, well, let's read it first. F is a function defined on some interval from a to infinity. Then we're going to say that the limit of the function is infinity as x approaches infinity if for all m greater than 0 there exists an n greater than 0 such that if x is greater than n, then the output f of x is greater than m. All that means is if we plug in a number that's large, we can make the output be large, and if we plug in a number that's larger, we can make the output get larger. And so we can make the output as high as we want by making the input higher and higher and higher. So let's look at a function that has that. Let's f of x, right? So as the input gets larger, the output gets larger. And the m and the n are just numbers to make this more precise, but that's the basic intuitive definition. Now, limit properties. This is how you actually prove some of these things. This is how you are able to evaluate limits of functions. So we have, the answers are on the back, but I have to swap back and forth, so I'm just going to say the answers as we get to them. So the limit of a constant as x approaches a number, well, I don't care what you do with x, there's no x here in this expression, so the limit is just going to be the constant itself. So the limit of a constant is a constant, the same constant. It's like the limit of 5 as x approaches 2, it's 5. There's no x's anywhere, right? The limit as x approaches a of x, well, I can make x really close to a down here, and what's going to happen to x? It's going to get really close to a, and so we're going to say that the limit here is a. Over here, the limit of a constant times a function is the same as the constant times the limit of a function. You can just move the constant out front. The limit of a product of two functions is the product of the limits of the two functions, provided they both exist. That's the same thing here. The limit of the quotient of two functions is a quotient of the limits of the two functions, provided that the limit of the bottom function is not 0 and they both exist. You can move the limit inside of a power or inside of a root as well. And there's the answers there if you want to check me. Okay, so those are useful. Those are how you evaluate limits. Now this is the most useful property. This is what you're going to use all the time, and this is what you should use first off, you know, in your class if you're trying to evaluate a limit, or even if you're using this in the real world. I want to give you a high five if you're using it in the real world. You're just gonna plug a number in and see what the output of the function is, and that could tell you the limit right away, right? So the direct substitution property is basically exactly what it sounds like. You're going to directly substitute that a value into the function and see what its output is. So this says if f of x is a polynomial or rational function, then the limit of f of x as x approaches a equals f of a, provided that f of a exists. Now, a rational function, this is just saying, is a ratio of two polynomials. But you basically, all you have to remember is just plug in x equals a into your function, and if it's like, if you don't divide by 0 and if everything works out and you get a number, that's the limit of the function. So this is the most useful property, the direct substitution property. And an example would be, okay, here's our function, like x squared plus 2. And somebody may say, hey, what's the limit of your function as x gets close to 4? And you're like, oh, okay, f of 4, well, it's 18. And they're like, you're good, you're smart, right? You didn't break out the limit properties. I mean, you could have said, okay, the limit of this, it's a sum, so it's a sum of the limits. The limit as x approaches 4 of 2 is 2, and the limit as x approaches 4 of x squared. Well, you just you move that in through the power function, right? And so the limit of x as x approaches a or 4 in this case is 4, squared is 16, plus 2 is 18, and meanwhile the guy's who asked you that's going to be like, what are you talking about? Just plug it in, right? So that's what you should think of first. All right, this says evaluate a limit at infinity of any rational function. Now these are tricks. These are like, okay, you got a tricky limit, right? Because the teacher is going to give you these, I don't know, to make sure you remember the properties or something, but basically here are some tricks. So this works. You divide the numerator and the denominator by the highest power of x in the denominator. So in this case, we have this rational function, two polynomials. We see the highest power of x in the denominator is x squared. We divide the top and bottom by x squared, and if you break up this division, you're going to see that 3 is going to be by itself, and then you're going to have like a minus 1 over x and a minus 2 over x squared, and then you're going to have 5 by itself, and then you're going to have like a 4 over x and a 1 over x squared. And as x gets really, really huge, those things that have an x in the denominator on the top and bottom are going to go to 0, and basically become 0, and then you're going to have just 3 over 5 left, and that's the actual limit of this function. Let's plug this function in and just check it out here. We got 3x squared minus x minus 2. And we're asking, well, 5x squared plus 4x plus 1. We're asking, what does this function do? And it's a doozy of a function. I mean, look at this. This is an interesting function. But basically, we're asking, what does this thing do as x gets really, really huge? This was as x goes to infinity. So we can plug in a number. We can plug in 1, and the function is 0 there. Okay, that's cool. Let's plug in like 5. Okay, it's 0.47. So as x gets bigger and bigger, right? Let's just make a x prime variable and have this evaluate, and then we can play around here and just make this bigger and bigger. You can see that as I make this bigger, the output, you know, it's approaching something and it's slowing down, and I'm making this really big. And it seems to be, you know, slowing down and just approaching one number, right? So we're making x get larger and larger and larger. Using this trick, we know exactly what the limit is, though. We don't have to like test it out. We know exactly that it's 3 over 5. So if I just evaluate 3 over 5, that is 0.6. And so you can see that is the limit of this rational function. So that's a trick, good trick. All right, rule for calculating limits as x goes to infinity or negative infinity. We just use this. So I should have put this note card first, but basically it says if you have 1 over x to a power and you make x really, really large, and that power is positive and a rational number, then this thing basically goes to 0. So that's what happened to those other terms before they just got knocked out and became 0. And this is basically saying the same thing, but it has to be a little careful because we're making x large negative, and so you want this to be defined. You don't want to have like the square root of a negative number and deal with imaginary numbers and all that, because we're dealing with real stuff here, not imaginary stuff. So do not attack me. I know imaginary numbers are real. So anyways, all right, here's a use of limits. And boy, I should have started the video off with this, but hey, we're getting here now. So vertical asymptote, you're probably aware of it, but here you're going to see the definition of it using a limit. So that's kind of cool. So we say x equals a, or just the number a, is a vertical asymptote of f of x if and only if the limit of f of x as x approaches a from the right or left side equals plus or minus infinity. So an example is, a great example, classic, is 1 over x. And I would say there's something going on here when x is close to 0. I mean, when x is equal to 0, this function is not defined. But remember, with limits, we don't care if it's equal to 0. We just want to know what's happening when we get really close to 0, right? So as we approach 0 from the right, the function shoots off to be really positive, also almost going to infinity, or is going to infinity, really. And as we approach 0 from the left, the output is shooting way down here, going to negative infinity. And so we would say that 1 over x has a vertical asymptote at x equals 0 because the function, the output, goes to plus or minus infinity. So there you go. There's a use for limits, vertical asymptotes, which are pretty cool things. Here's another use, horizontal asymptotes. And we kind of already saw that with our as x goes to infinity or minus infinity. So we're going to say the line y equals L, or the number L, is a horizontal asymptote of the curve y equals f of x if either as x goes to infinity, the output goes to L, or as x goes to negative infinity, the output goes to L. So remember our function we had before? I'm going to undo. And with this guy, we have a horizontal asymptote of 3 over 5, because as x goes to infinity, as I make this test point x really, really large, the output of the function just gets closer and closer to 0.6. So that is a horizontal asymptote, and I could graph that, right, and just say graph 3 over 5, and I'll make that orange. And you can see that, like, as x goes off here to positive infinity, the output of the function gets closer and closer to this orange line. So that's a horizontal asymptote. Moving on, we're making good progress here. All right, here's a tricky function. Find the horizontal and vertical asymptotes. And so we're going to use some tricks on this one. Let's just plug it in, though, to get an idea of what it looks like first. So for this, we have the square root of 2x squared plus 1 divided by 3x minus 5. Okay, we'll get rid of this stuff. And, okay, before, remember we had a horizontal asymptote, and actually the left and right side were going to the same number, but now it looks like as x goes to infinity, we have the output going to one number, and as x goes to negative infinity, we have the output going to a different number. So let's take a look at how that could be possible. Okay, so we'll solve this. What is the limit of this, right? So this says we'll use our trick, divide x, or divide the top and bottom by the highest power of x, which is just x in the denominator. So we do that. And here we have x, and we have this square root above it. We can actually square x and take the square root. And because x is going to infinity, the square root of x squared is actually just x itself again. So this is totally valid. We can do this and bring it inside the square root. Meanwhile, down here in the denominator, it cancels out with the x in front of the 3. But we end up with this 5 over x, and we know that as x goes to infinity, this 5 over x is going to go to 0. And meanwhile, up here, the x squared is going to cancel out. We're going to be left with a 2 and a 1 over x squared. That's going to go to 0. And I should have written limit over here on this side of the equality, because the limit, we haven't taken the limit yet, right? So be sure to carry that along. But basically now we just say, hey, let's try taking the limit of the top and bottom and see if they're defined. And if it works, then we're good. And it does. These go to 0. And we're left with square root of 2 over 3. So as x gets really large, we're getting 0.47 out of this. And if we look at what is the square root of 2 over 3, it's 0.47. So it looks like that's good. Now, how could it be different as x goes to negative infinity? Well, this is kind of crazy, right? But let's see what happens. Now, we do the same trick, divide by x, top and bottom. But this time, follow my chain of reasoning here. The definition of the square root of x squared is the absolute value of x. So we'll look at the xy plane of the square root of x squared. And that should look familiar. We'll make another function, absolute value of x, and graph that. And you should notice that they are exactly the same. So the absolute value is in red. So the square root of x squared is the absolute value of x. That's the first thing we need. Now, by definition, the absolute value of x, if x is negative, if the value of x is negative, it could be like -3, you know, hiding in here inside the variable, right? The absolute value sees that and says, I know you're being negative. And I'm only about positive thinking here, so I'm going to throw myself out the window and throw a negative out in front of you, just so that whenever your actual value, which I know is negative, I'm watching you, whenever that comes out, the two negatives are going to cancel, and we're going to stay positive here, right? So this is only for when x is less than 0. This chain of reasoning works. Now we're going to multiply both sides by -1, and we're going to see that we're going to end up with an x equals the negative square root of x squared. And so that's what we do. We just substitute this x here is equal to negative square root of x squared. Now, it makes sense to me now, but if it doesn't make sense to you right now, I don't feel bad. It took me a moment to understand what was going on here, but it works. So now the only difference between the top and bottom is we have this extra minus out here. We keep that around. We do the same thing. We take the limit of the top and bottom, and we get the negative. So we get negative root 2 over 3. So that's why we have two horizontal asymptotes for this function. And if I make x really negative here, our test point, okay, one of these days, there we go. So if we make this more and more negative, you can see the output of the function up here is approaching negative 0.47. So that's a horizontal asymptote. So this function has two horizontal asymptotes. Pretty cool. Another trick. You see something crazy like this? Multiply by the conjugate. All the conjugate is you flip that sign there. And we're multiplying by 1 here. This is like a math trick. You know, you see all this stuff, you're like, what the heck? How can we do this? How is this the same as this? But the same thing divided by itself is just 1. And so we're just multiplying by 1, and anything times 1 is itself again, right? 5 times 1 is 5. This is a trick. Try it out. The reason we did this is because, you know, you tried direct substitution and you plug in a 3 here and you're going to get 3 minus 3 on the bottom is 0, undefined. So we needed some help here, and multiplying by the conjugate helps. So we'll see that in an example coming up here. Right now, actually, so we have these tricky limits. So as x goes to infinity, here it's kind of hard to say. This is going to infinity, but this is going to negative infinity. So is it 0? What is it, right? And over here it's kind of hard to say because, well, maybe less hard to say because this is going to infinity really fast. This is going to negative infinity, but I have a feeling that the square is just going to shoot off faster. But we have to prove it. We have to use these tricks, right? So, of course, the first one, multiply by the conjugate. When you have nothing left, you can do that. And we see, okay, we get this times this, the square root's gone. We have this times positive x, this times negative x, cancels out. We have negative x times x. We have minus x squared. And if you look at the top, x squared minus x squared, gone. We're just left with a 1. And on the bottom, it's all positive stuff. You know, as x gets bigger, the denominator gets bigger. We're dividing by a larger and larger number. That means the whole thing goes to 0. Now for the bottom, we're not allowed to split it up and take the limit of the sum or difference, each part of the difference, because if we evaluate these now, as x approaches infinity of x, that's just going to be infinity, and infinity is not a number, so those really don't exist. So what we have to do is factor it, and if we bring out an x, we see we have the limit of a product of x and x minus 1. And as x gets closer and closer to infinity, both of these things are going to get really big, and so the limit is infinity as we intuited before, right? Moving on, here are some trig limits. Now, I'm going to just ask you to remember these. There's ways to prove them, but for time, these are classics. Sine of x over x, as x goes to 0, it turns out it's 1. And 1 minus cosine of x over x, as x goes to 0, it turns out it's 0. We'll see something called L'Hopital's rule that helps us verify these. and make it straightforward y. And there's also geometric proofs if you're interested. Here's the same one. I think I just kept it because it has this cool drawing in here. Very surprised that this is 1. Here's the same one, except now it's a little different. We have a 3 inside here. So as mathematicians, very tricky mathematicians, what do we think? Multiply by 1, which in this case is multiply by 3 over 3. We use a limit property, bring that 3 out front. And now you see we have something that looks very similar, right? As x approaches 0, sign of blip over blip, right? So we can make a substitution and basically end up at sine of u over u, and this is as u goes to 0, and that's just 1 again, so this turns out to be 3. So there's a technique, you know, to change these and be tricky and try to get you guys, and then there's a way to solve them. You make them look like something you already know and understand. Now, here's another one. This is a good one. So there's something called the squeeze theorem, and when you look at this, you're like, what the heck is going on? Because as x goes to 0, this thing is oscillating wildly. This is going to 0. But we know something about cosine of anything, and that's that the output of cosine is always between -1 and 1. Now we're trying to evaluate the limit of this function x squared times cosine of whatever's in there. So all we do is, first we write something that's true, right? The output's between -1 and 1. Then we multiply everything by x squared to make the inside part look like the function whose limit we're trying to evaluate. And we have to multiply the left and right here by x squared as well. And then we just take the limit of this kind of each part, and we know that the limit of negative x squared as x goes to 0, that's just 0. And x squared as x goes to 0, that's just 0. And so if this thing is sandwiched between these two things, and this is also called like the sandwich theorem as well, then if it's sandwiched between 0 and 0, the thing's got to be 0 itself. So by the squeeze theorem, by the sandwich theorem, this limit is 0. So that one is very useful. And let's look at it, because that one's kind of cool. So let's write our function. First of all, let's just look at cosine of 1 over x, because that's just kind of crazy too. So yeah, you see this and you're like, what the heck? It's oscillating like crazy, right? Because 1 over x is getting really, really huge. But if we put an x squared out in front of it, and you look at that, you're kind of like, hey, yeah, it seems to be kind of controlling it, right? And so I could even make this like, let's make it like let's make this get wavy faster. So we want 1 over 5x, wait, 1 over 3, 2x, oh, 2x here, yeah. Bear with me, I have an idea, I think, of what I'm trying to do here. There you go. So it's really wavy. Oh, pardon me. But if we throw this x squared out front, there you go. That's what I wanted to see. Basically, it's being squeezed by positive x squared and negative x squared. And I'll make those red. And so you see our function, the black function, is being squeezed between these two red functions. And so we can say that as x goes to 0, our function also goes to 0. So the squeeze theorem is pretty cool. Here's another use of limits. We can say f is continuous at x equals a. This is a definition of what continuous means. If the limit of f of x as x approaches a equals f of a. And so what is this telling us? Well, it's basically saying if we change the input of the function a small amount, the output should only change a small amount. Because remember, somebody has challenged us to get really close to this limit. And so we've said, yeah, you stay within these boundaries, right? You're going to be as close as you want. And so the limit in this case is f of a. It's actually f of the value. So here's another one. Let's see, f is continuous at a point when. So we have the same definition of continuous. Oh, this is kind of a proof. So prove x squared is continuous at x equals 0. Here's a proof. We're going to take the limit of the function, right, as x approaches 0. That has to equal f of 0. So in this case, f is x squared. 0 squared is 0, so this is 0. And also this limit, we can bring this in the power, right? And the limit as x approaches 0 of x is 0. Squared is 0. They're both 0. F is continuous. And now I'm going to be arrested or taken away in an ambulance, if you can hear those sirens. Sorry. Finally, last note card. We did it. I hope my microphone has been recording this whole time. It didn't record the first time. F is continuous over an open interval when. This one's kind of obvious. F is continuous over the interval if and only if f is continuous at all the points in the interval. That's what this symbol soup is saying. If it's continuous at x equals a for all a in I. That's it. Limits. We did it. I can't believe we did it. Limits are a tough thing. These epsilon delta proofs are hard. They're harder for functions that aren't linear. You don't have an exact rule. And you know, I feel for you if you have to do some of them, but there are some good resources. And if you look at proofs, you'll see the pattern in there and you'll be able to do it. I believe in you. So anyways, that was limits, and I'll see you in the next one.